In this video, we are going to discuss about the common gate amplifier. So on the completion of this common gate amplifier, the students will be able to find out the ideal maximum voltage for the common gate amplifier. And this common gate amplifier, you can see the circuit here. So gate terminal is grounded. So in common gate configuration, this gate potential which we are applying at the constant potential, there will be the increase in the input voltage and in the positive direction whenever there is an increase in the negative gate source voltage. When the ID reduces by reducing this ID RD, then we write this VD is equal to VDD minus ID into RD. Then the reduction in the drain current results in the increase in the output voltage. So this is the basic circuit, and here you can find out the hybrid model of this common gate amplifier. So VI RS, then RD GM into VGS. Since this current is flowing from the drain to source, you can be identifying this current direction is along the drain to source, which is GM into VGS RD, and here one is V0. And next one is we are going to calculate the input impedance, output impedance, and voltage gain. So we know that is input impedance, that is nothing but ZI dash is equal to VI divided by I. So here we are writing that ZI is equal to RS parallel ZI dash. So this time we are simplifying and we are writing this equation as IRD is equal to I plus GM into VGS. I is equal to IRD into GM into VGS. So IRD is equal to VI minus IRD divided by RD, and here VI by I is equal to 1 plus RD divided by RD divided by 1 by RD plus GM. So we are taking this, simplifying this term by taking the LCM, and we can cancel the factor, that is RD and RD. So we will be getting the denominator terms will be cancelled, and finally we will be getting RD plus RD divided by 1 plus GM into RD. Then we are substituting those values in the above equation, that is ZI, which is equal to RS parallel ZI dash, which is equal to RS parallel RD plus RD divided by 1 plus GM into RD. In the case if RD is very greater than RD and GM into RD is very greater than 1, then we can neglect this term, so that we will be getting that ZI is equal to RS parallel RD divided by GM into RD, which is equal to RS 1 by GM. And to calculate the output impedance, we are giving that Z0 is equal to, there is only the drain resistance, that is RD, as well as small resistance RD. So in writing Z0 is equal to RD parallel RD. If RD is very greater than RD, then you can write this equation as Z0 is equal to RD. And next, voltage gain. Voltage gain, you know, that is AV is equal to V0 by VI. VI0 is equal to minus ID into RD. That is according to Ohm's law, we are writing as V is equal to I into R. So output voltage, you can write it as ID into RD. So in this equation, you are writing the output voltage as well as the input voltage. So in this input voltage, you are writing as VI is equal to minus VGS. When you are applying the KVL to the outer loop, after the simplification, that is AV is equal to V0 by VI is equal to minus ID plus RD divided by minus ID into RD plus RD divided by 1 plus GM into RD. So you can write this equation as is equal to RD of 1 plus GM into RD divided by RT plus RD. If this RD is very greater than RD means, and also GM into RD is very greater than 1, then we can write this equation as AV is equal to RD of GM into RD divided by RT is equal to RD. That is, we are cancelling this RD and RD. And here we can find out the exact value and the, if it is greater the value. So ZI exact value is RS greater parallel with RD plus R0 divided by 1 plus GM into RD. In case if it is RD is very greater than RD means, then RS is parallel to 1 by GM, and Z0 is equal to exact value is RD parallel RD, and if it is greater means it becomes RD. And voltage gain, RD into 1 plus GM into RD divided by RD plus RD is the exact value, and if it is greater means we will be neglecting this RD term, so we will be getting GM into RD. Thank you.